I have to say, Lewis, this is my favourite.
Okay, right.
Because what this tube shows you is...
So David, we've got some quite expensive equipment out on the table here. Mm-hmm. Could you talk us through what we have and maybe how we can actually set it up?
So we've got some Teltron tubes here. All of this is to try and understand better what happens when we've got electrons flying from a cathode ray tube, and we can then get experiments to see what happens under different conditions.
Okay.
So the first one we've got here, this is the original Teltron tube in some ways, because in there you can see there's a Maltese Cross. Now, anecdotally, the reason for that is that back in the beginning when they first made one of these, he had a medal on his desk when he was making the piece of equipment, and he put that in as a way of sort of blocking the route that the electrons can take across the Teltron tube.
Yeah. Okay. So we've got this kind of power pack over here, EHT.
So the EHT, that stands for extra high tension. The T tension there is because in French voltage is tension, which is tension, which is why we use that for the EHT unit.
Okay.
It's worth looking here because you can see we've got actually two sets of connections. We've got the high voltage connections here, but these yellow ones here are low voltage, only 6.3 volts, but that's an AC supply, and we need that to be able to use the Teltron tube because it works by thermionic emission.
Okay.
So this, if you come in close here, you can see we've got an electron gun just here, and the back of that has got the cathode, but the cathode has to be hot. And it's done by basically a bulb behind it, making it hot.
Okay.
So if I show you, if I switch the EHT on, I've got no high voltage, so that's at 0 kilovolts.
Yep.
But my 6.3 volts has already turned on a bulb behind the cathode, so it's heating it up.
So at the moment, this it looks like there's light coming from the back, and that's basically kind of a light bulb. It's just making stuff hot.
Yes.
Cool.
Now what I can do is between the black connector here and the red connector here, I can now start to put a high voltage.
Okay.
Positive here, because I want to attract the electrons from the cathode, accelerate them, make go really fast, and then they're going to miss and come through the big hole and just travel across the tube, which if I turn it on, you turn up the voltage, you can see the white shadow now becomes a green glow where the electrons are firing across the Teltron tube, hitting the phosphor screen and emitting green light as evidence that the electrons have arrived.
So it's not that electrons are green, it's just that they're hitting that screen and we can tell where the electrons are landing because they're energizing that surface and then that emits visible light.
Excites the phosphor, which then de-excites and emits photons of light in the green frequency range. Okay,
and there's a shadow there that we can see, and we've got another shot here in the darkened room to kind of really sort of show this off. How could we have this kind of shadow where we see that Maltese Cross?
And you'll see that the shadow matches the same as the light shadow.
Okay, so this is just a light shadow at the moment.
And then the electrons will match that same shape,
showing
that the electrons are travelling in straight lines, hitting the obstacle. The ones that hit the obstacle are blocked, and the ones that don't hit the obstacle carry on straight past, and they're the ones that hit the screen.
And there's a red connector which is connected onto that metal Maltese Cross. So what's that?
So that's because if you don't connect the Maltese Cross, the electrons will build up on the Maltese Cross and will start to deflect the electrons away. So that's to allow the electrons that do hit the Maltese Cross to flow away on those through this wire back to the power supply.
Cool. Okay, so it's kind of basically earthing it.
Yeah.
And we can see that if you have, if we unconnect that at the bottom, we can see that over time, the cross that we have there gets slightly more fuzzy. So it's more like a sort of a 4-leaf clover. That's right. And these can be deflected by a magnet as well.
So one of the nice properties of electron beams is that they will be deflected by a magnetic field. So here I've got some neodymium magnets. If I bring that in towards the side, it doesn't have to be even very close. The field is already deflecting the path of the electrons.
Yeah.
And if I bring it closer, that effect becomes greater because the field is stronger. And you can actually make quite a distinct effect with that magnetic field. Not distorting the image, it's distorting the path of the electrons, forcing them to go into the curved path as they go into the magnetic field.
Okay, so a Maltese Cross, I think this is a fairly common kind of tube that a lot of schools do have, and I think it can be used, at GCSE as well as A-level.
Yes, it's nice to use at GCSE from the F equals BIL and getting them to sort of get this idea of electrons being deflected, and the same is happening inside the wire with the electrons experience force, but up at A-level for the sort of more involved calculations that go with it.
Brilliant. Okay, so that's the first one. We've got quite a few more tubes on the table, don't we? So which one should we do next?
I think the next one to do is to see how we can take an electron beam and we can use an electric field and a magnetic field to deflect that. We saw it sort of qualitatively with the bringing a magnet. When we've got the Teltron tube with these Helmholtz coils, we can start to create a defined magnetic field with a current in these coils making a uniform magnetic field over the region of the Teltron tube.
Okay, so the setup, we've got another EHT power supply there, and that's connected to, a bit like we had last time, we've got...
The connections are exactly the same as last time, Lewis.
Okay.
So again, we've got the low voltage connection, which is going to heat the cathode at the back of the electron gun, and we're accelerating with the positive at the other end of the electron gun. The only difference is that this one is going to make a letterbox or a postbox shaped beam rather than having a big circle so that they go across the whole tube. We're going to just create a plane of electrons going across the tube.
Okay, that all makes sense so far.
If you look in the middle of the tube, you can see there's a white grid, and that grid is covered again with phosphor. This time it's blue phosphor rather than green phosphor, so it's going to excite with blue light.
Yeah.
When the electron hits that grid, it's going to show you where the beam has hit the grid, and you can trace the route that the electrons are taking. It's probably easiest if I just show you what that looks like. So if I put the electron beam on, you can see that there's a blue line across there showing that the electrons are travelling in a plane across the tube, striking the grid across what we probably would call just the zero axis.
Cool, okay, so that all kind of makes sense. And I guess if you're demonstrating to a class, the lights off a bit to kind of really show that, and we can again get some extra footage, but I can see it quite clearly at the moment. And this Helmholtz coil,
Okay.
So there's basically a coil on one side and a coil on the other.
Mm-hmm. So we've got a current in the Helmholtz coil on this side that will then carry on and be in series with the second Helmholtz coil on the back, making the region between the two will have the uniform magnetic field.
So this is basically our kind of solenoid, and rather than just having kind of one coil where we have that kind of uniform field in the middle, we've basically got half a solenoid there, the other half there, and then there's going to be these uniform field lines that kind of go through the middle. So we have that uniform region in the middle. Good. Now, something you mentioned that I'd never really considered was about if these are wound clockwise or anti-clockwise, and how that's important.
So often it's better just to do it by trial and error.
Okay.
Because the current is going to go in and around this one.
Yeah.
Because the coil on the other side is mounted the other way round, you have to come from the right-hand Z hole of here and take that into the Z hole on the back of the Helmholtz coil.
Okay.
But if you set it up and it's not right, the deflection of your beam is going to be all mixed up. Just switch them over and you'll find it'll solve itself.
But effectively, if you had both of those coils being identical, they'd both have maybe like a kind of a clockwise twist on the way that they're formed.
Yep.
And then if you just had the one on the other side, if you're mounting it 180 degrees, it's almost like twisting the other way.
That's right.
But again, this is something that when you're setting it up, or if the technicians are setting it up, just to sort of have a play around with, and you might need to just change the way the wires are connected.
That's right.
Cool.
Shall I show you what it does to the beam when we
let's do it. Let's get
the
the proper physics happening.
So I'm now going to switch on my low voltage DC that's connected to the Helmholtz coils. Now as we increase the current, you can see that that electron beam is being deflected upwards, and because it's a magnetic field we can see that that's a portion of a circle.
Okay, yeah. So it's not a parabola, it's a circular path.
Yeah, and if I push it sort of right up there, that becomes quite clear. I think that is a circular deflection.
So a constant radius of movement.
And that's because the magnetic force is always perpendicular to the direction of the travel. Therefore, you're going to get your centripetal force causing the circular motion.
Perfect.
That's only half the story, though. Lewis.
Okay, so we haven't quite finished with this one then.
No, because this tube will also allow you to do an electric deflection of the beam as well. And if you look inside, you can see that there's two metal plates, one at the top and one at the bottom, connected to a separate EHT supply.
Okay.
So that's connected to this supply here, which is going to put an electric field between those two metal plates.
Yeah.
I'll switch it on, it makes it probably easiest to see. So I can now see that I've set it up so this time the bottom plate is positive and the top plate is negative, and that's deflecting it. But you notice the difference in shape?
Yeah.
This time it's not a circular path, this time it is a parabolic path.
So this is more like the path that maybe a ball would take in a gravitational field?
It's exactly the same shape, because the force is always acting downwards, 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 wherever the trajectory is, always a force downwards, as if you were throwing a ball with the gravitational field always downwards.
Cool, okay, good.
The real interesting trick is, though, we can do both of those at the same time. So at the moment, I've got the electric field deflecting it downwards, but if I put the magnetic field on as well, I can bring that beam back so that the magnetic force is acting upwards and the electric force is acting downwards, and now the beam has gone back to travelling straight through.
Perfect.
Now there's two uses for this. One is that we can use that now as a velocity selector, because the electric field force does not depend on the velocity of the electron, but as the magnetic field does from F equals BeV.
Yeah.
So we can pick the ratio of the magnetic to electric fields to allow just one speed of electrons to go on that straight across route. So if I change the accelerating voltage of the electrons, so I'm leaving the electric and magnetic fields alone. Now what I'm doing is I'm changing the accelerating voltage
and we get a different path. So when you've got a different potential difference between the cathode and the anode, which is accelerating it, we're giving them more electron volts of energy, I suppose. And if they've got more energy, there's greater kinetic energy and a greater velocity.
And therefore the path you get is different, and you can select the one you want is the one that goes straight through.
Cool.
You can also use this for the Thomson experiment because it gives you access to the charge to mass ratio of the electron, and this was the experiment they did to try and work out what the charge and what the mass of the electron was when they were first investigating.
But as I understand it, they could just look at the ratio between charge and mass, but they didn't know the exact charge or the exact mass.
And that's why Millikan had to come along and do his experiment to help them out.
Okay, so we don't have that. I do have another video actually of Millikan's experiment to set up. But so this one over here, so we've got two EHTs. I think a lot of this equipment's actually quite expensive, and I think you're quite fortunate to have access to all of it here. But I'll put the prices up on the video for how much different things cost. And I think even the stand here for the tubes, I suppose they're not made in great numbers, so they can sort of demand a high price for them.
They're expensive, but often schools have them hiding in the back of cupboards.
Yeah.
People don't quite know what they're for. And then once you've seen what it's used for, the glass tube might be in another cupboard. Go and have a look. It's amazing what's hiding in the cupboards.
I think there's definitely a lot around the country.
Okay, so not being used.
Yeah, so we'll come around the other side now. We've got a couple more. I think actually that the torch is a great tip for when you're teaching, isn't it?
Yes. Now, the torch is here because this tube here, the effect is quite dim, because what we're going to do is inject electrons directly into a gas which is going to glow, rather than a surface that we've had over there with phosphorus. This one's going to have a gas which is going to become ionized and excited, so we can see the actual beam the electrons take through the tube.
Okay, cool.
But because we're going to have the lights turned off, the torch is good to find where the power supply is so we can turn it on and off.
And that saves having to get up and down to turn the main lights on and off. You can just use a torch just to illuminate that. Okay, so this one here, We don't have an EHT, do we? Is that
No.
right?
This is super important, Lewis, because we call this the fine beam tube, and a fine beam tube uses a HT power supply rather than an EHT. So we lose the extra. This is it's still high voltage, but it's only up to about 350 volts.
Okay.
However, the current is much higher. And this one you've got to be more careful with because that higher current can actually hurt you.
Okay, so this is the one that, again, you know, if you're a teacher or technician, you know, it's worth kind of doing a bit of research. I think you've got shrouded leads on this as well to kind of stop any metal connectors kind of...
We've used shrouded leads for all of these experiments. Maybe it's worth just showing what that looks like. So there's the connection underneath. This is all switched off, so I'm going to just show you how it works. So there's the bare metal being covered by a plastic shroud that only comes back when you push it in to make the connection.
And that just means they're not like the kind of normal kind of just the normal kind of leads you get in a science lab where you've got the exposed metal. This is just that extra level of protection to hopefully stop you receiving an electric shock. Yeah.
As soon as you pull it out, you can't touch it.
Cool. Okay. And I think that's important, isn't it? If you're going to be setting this up.
Always use the shrouded leads.
Yeah.
Always use them.
Cool.
Shall I show you this this bit of kit then?
Yeah, let's have a look at the kit first of all in the light.
So if you look in the centre there, you'll see it looks slightly different. So here, on the ones we've shown you so far, the electron gun has been here. That's not true on this one. They're actually inside, and there's actually two. One is pointing horizontally, and one is pointing vertically upwards.
Okay.
So there's two. And if you look on the back here, there's a little toggle switch here that allows you to select one and the other.
Okay. Yeah.
So when we put the power supply on, again, this takes a little time to warm up. But you can already see, if you come and film just here, Lewis, you can see the little light bulb at the back there.
There's a little bit of glowing.
You see how small it is?
Yeah.
Because this is going to actually inject the electron beam in. Now if I switch the switch, that one will go out, and it'll energise this one at the back of the horizontal one.
Okay, it's a little bit difficult to see, but I'm sure I can get some extra footage of that. Yeah.
Okay. Now, this is the horizontal beam. It's way too bright in here to see this. So I am going to need to go and turn the lights off for this, which is why we have the torch.
Cool. Okay, let's do that.
So if you look on the end here, you can see the little green dot.
Oh, yeah.
And that green dot shows you where the electron beam's arriving. Now if I show you inside the tube, if I take the torch away, you can see there's a very faint beam of electrons.
Yeah, so I can see the gas has been energised in a line. There's this kind of excited. So it's, rather than it being the screen that's glowing, we can actually see the gas inside glowing itself.
That's right.
Yeah. Okay, that's good.
Now, again, with the same as we've just had with the Teltron tube, this one has got the Helmholtz coils being powered by the low voltage power supply.
Okay.
Now, when I turn it on, what you can see is that beam,
Oh, yes.
in 3D space, is now being deflected into the perfect arc of a circle.
So again, that's what we had on the previous one, where it was on the, we could see just like the line on the kind of grid.
Yeah.
But now we can see the same thing just like in the middle of, in midair.
In midair, in space.
Yeah, in space, yeah.
So now I'm going to flick to the other beam, and this one will slowly disappear as the cathode cools down and the beam's no longer present. Now as the other one warms up, this time the beam is being injected vertically downwards.
Okay.
And then when I put you can see, because it's been injected into the field, it forms a perfect circle. The stronger the magnetic field, the tighter the circle.
Oh, yeah. So it's quite faint to see still. Even in real life, it's quite faint. And I think that's why you need to have a really good darkroom, isn't it? And get as much of the light blocked out. But you can see there's definitely a circle there. Yeah.
And also, if I change the accelerating voltage, you can also change the diameter of the circle with the accelerating voltage. So as I increase the accelerating voltage, the speed has increased.
Yeah.
The circle is bigger. If I decrease the accelerating voltage, the speed decreases, so the circle gets smaller.
Yeah.
Turn that off and that off. I'm just going to turn the lights back on.
So what's the name of this tube that we have here?
So this is the fine beam, because the beam of electrons is very, very tight. And that's why it comes from such a small electron gun.
Yeah.
And why you need to use the HT power supply, because it's smaller, but it's going to have a higher current so that you can get the actual gas to glow, rather than the other tubes we've looked at where the electrons are arriving at a phosphor screen.
Yeah.
So it's arriving, and whereas on this one it's actually passing through the gas and energizing the gas as it goes through.
Brilliant. And then we have yet another one over here, don't we? This is like the fourth one that we've got.
I have to say, Lewis, this is my favourite.
Okay,
because what this tube shows you is the particle wave duality. Yeah. So you've got electrons here behaving with a de Broglie wavelength.
Okay.
And this is just at the very sort of basics of what actually is going on in physics in quantum. And I love this tube.
Okay.
So this one is back to the original style of tube. So we've got an electron gun at the back here. So there's the thermionic emission from the hot cathode. But this time, the electrons are going to be fired at a target.
Okay.
And that target is graphite.
So the target is actually, let me just see if I can see, it's quite a small target inside.
Yep.
And this is a vacuum inside, is that right? Yep.
So the electrons this time, rather than coming directly from the gun and hitting the phosphor screen, they're going to go through a graphite target. And the graphite is going to act as a diffraction grating.
Okay.
So the electrons are going to diffract through the gaps in the lattice of the graphite, and then because of the de Broglie wavelengths of those electrons, they're going to produce a diffraction pattern. If you did this with your laser beam into a diffraction grating, then you get single dots. But because your graphite is in 3 dimensions, there's a 2-dimensional, so it'll do a diffraction grating in all orientations.
Yeah.
So we're not going to see dots, we're going to see rings.
Okay, cool.
So when I turn this on, you can see the heater is on, the electrons are going to be produced, but this time the electrons are passing through that graphite target, and what we'll see on the screen here is not a dot of electrons, but we'll see rings of electrons.
Okay. So again, I think with the lights off, you really see the effect quite nicely. There we go.
So those rings there, Liz, that's the evidence we've got of the electrons, which we often consider to be particles, at these high speeds now by the de Broglie wavelength are behaving in a wave-like matter.
So this isn't like a green laser light that's being shone through a diffraction grating. This isn't light. This is electrons.
No. So in the gap between the screen and the graphite there, that's electrons travelling.
Yeah.
And they're travelling, having gone through and diffracted, to mean that there's areas on the screen where there's the high probability of arrival, there's areas on the screen where there's low probability of arrival, and you get this diffraction pattern.
Okay. And can we change that diffraction pattern at all?
Of course, because we can change the de Broglie wavelength.
Yeah.
And we change the de Broglie wavelength by altering the accelerating voltage. So if I decrease, I've made them travel slower, and if I increase the accelerating, I make them travel faster. And if you increase, you're going to make the wavelength shorter.
Yeah.
And if you slow them down, you're going to make the wavelength longer.
So in this one here, we accelerate the electrons as particles. They travel as a wave, and they diffract through that because of their wave-like properties, and then they interact like a particle again on the screen, roughly, isn't it?
Yes.
Yeah. So
you're accelerating them, and we do that in the normal way with the kinetic energy.
Yeah.
And then the wave-like behaviour happens as they go through and do the diffraction, and that will continue until they hit the screen, and that's when they are doing a collision, and we're back to understanding as particles again.
Brilliant. Right, let's turn the lights back on. So these tubes then, they're called Teltron. I think what are the manufacturers?
The manufacturer, yes.
And that's why collectively they're often known as Teltron tubes. We've got different ones here that show, like we've got the kind of the quantum nature and the kind of the wave particle duality. We've got stuff that we tend to do more in year 13, looking at charge to mass ratio and electric and magnetic fields. Any final advice for teachers or technicians if they're going to be using these in schools?
There is one really important thing, Lewis. Please don't be the teacher who has to go and embarrassingly say that you have blown the heating filament, because it's too easy to do. And it's when you connect, instead of the yellow to the low voltage, you connect the heater to the high voltage.
Okay.
Because the high voltage into the heater will cause too much current and you'll blow the heater.
And that's when you then find there's a tube that's just not emitting any electrons at all.
And you can tell if it's happened, because when you connect it to the low voltage, that little, the heater at the back won't come on.
Okay.
And sadly, that will mean that the tube doesn't work, and you'll have to go and explain that in a very embarrassed way to your technician.
Or just say that somebody else did it.
You would never do such a thing, though, would you?
No. David, thanks so much for showing me around these. I think that these are, if your school happens to have these, or if you're a student and you see these in your school, it's incredibly fortunate that you do have them. And it's a shame that if they exist in your school but they're not being used, that maybe it's just a case of spending a bit of time just looking at the equipment you've got and actually looking at the wires and thinking, where does what go where? And also I think there's going to be plenty of advice with cleeps or cleaps. Yes. I always forget how to say that. But they've got advice about how to use these safely as well.
Yeah, go and look in the cupboards. Often schools have them and just don't realise the experiments that you can do with them.
Brilliant. Thanks so much.